Hey guys, in this video we're going to be talking about how to determine the number of signals in proton NMR. So you're going to have unique protons in a given structure and you have to figure out how many signals would you see in a given proton NMR. And just to remember, you can have the homotopic protons, and if you do have any homotopic protons, they are going to be equivalent. If you have an enantiotopic protons, they are going to be equivalent, except if they are in the chiral solvent. And if if the question if the question doesn't really specify what type of solvent you're using, then always assume you are using a chiral solvent where enantiotopic protons are also going to be equivalent and will show up at the same place. And then you have these distereotopic protons. They are not going to be equivalent and they will have a different chemical shift. There are going to be times when you have two distereotopic protons just happen to be having the same chemical shift and showing up at the same place, but that doesn't necessarily mean they are equivalent. They're always going to be not equivalent, and obviously you're going to have different protons in there that will be giving you different signals. If you have hard time understanding these homotopics, enantiotopic, and distereotopic, make sure you watch my other video where I have explained these three in details. So I'm not going to be talking about the splitting patterns in this particular video. It's just going to be how to figure out the number of signals based on the magnetically different protons you have in a given structure. And I'll have in a separate video where I talked about the splitting, the number of peaks, and also the chemical shift of those protons. So I'm just going to be focusing only on the number of signals in this particular case. So let me take this first example. So I got a CH3, CH2, and CH3. And remember, if it's hard for you to figure out where the number of protons are, then you can always write down those protons. So I'll write down the protons for a few of those, but I'm not going to write down proton for every single one of them, just for the sake of time there. So we got three protons there, and then obviously we got two protons in the middle one. And then, well, what's happening there? Your metal protons are always going to be equivalent. So the metal on the first carbon, or another way of saying this metal right there, is those three protons are going to be equivalent, and the metal on the right side is also going to be, those three protons will be equivalent. But are those two metals are going to be equivalent to one another? And the answer is yes, they're going to be equivalent, because if I draw a line here, then this particular line tells you that the right side of the molecule and the left side of the molecule is actually the same, or there is an internal plane of symmetry in this particular molecule. And as a result, you will see only two signals, where one signal is going to be coming from these A protons, so let's call this A, and one signal is going to be coming from these B protons. So we'll have a total of two signals in there. Okay, what about this next one? So in the next one, I can clearly see there is going to be a internal plane of symmetry. And if I draw that internal plane of symmetry, it's going to be going like this. So I have the two protons on these methylene groups. So those two protons are right there. And these two protons are going to be the same, actually. So they will be showing up at one particular place. And then you got these three protons on those metal groups. They are also going to be the same with one another. So I can say those two are the same, and then I can also say these two protons are going to be equivalent. So you will again have only two signals at the end of the day. Let's try this next one. We have pentane in the next one, and there is again an internal plane of symmetry. So if I go ahead and draw that out, it's gonna look like this right there, not straight from the middle. And then the left side of the molecule is the same as the right side of the molecule. So I would say I have one type of proton here, so I'm not really going to draw the protons now. You want to be able to get in and have it off looking at the structure without drawing the protons. So that's going to be one signal here coming from those guys, and then I'll have another signal coming from these guys, and then I'll have another signal coming from these protons right there. So you'll have a total of three signals in this particular case. Okay, moving along, it's probably going to be a good idea if you can pause the session and figure these things on your own and see if you get those right. This next one does not really have any plane of symmetry. On the right side, I have this tert-butyl group, and on the left side, I got these two methyl groups. So there's really not any plane of symmetry, so don't take that as the same on both sides of the molecule. So as a result, I would have one signal coming from these protons right there. Remember, those two methyl groups would be the same, however. Then moving along the molecule, I would have another signal coming from this proton right there. How many protons you have on that particular carbon right there? Well, it's going to be only one proton, so it's going to be giving you a signal. And then I'll have another signal coming from here, another signal coming from that carbon. And then this next carbon that has three methyl groups attached to it does not really have any hydrogens on it. So we move on to these methyl groups. So those three methyl groups I have here, they're all going to be giving you, those protons are going to be magnetically equivalent. So I'm going to have the signal 5 coming from all those three protons. So I'll have a total of 5 signals in this particular one. Okay, what about this next one here? Well, you do have a lot of protons in there. I got two protons in every single carbon in this cyclohexane, but turns out this cyclohexane actually has an internal plane of symmetry. And if I draw it anyway, like I can draw it this way, then the left side and the right side is the same. Or I can draw it this way where the top and the bottom is the same. Or I can even draw it this way where, the top right and the bottom left is the same. So they're all going to be equivalent to one another. So as a result, you're going to be seeing only one signal in this particular case. Okay, what about this next one here? We have a cyclohexene, so there isn't a double bond indeed there. And when we're looking at these double bond, do we have any internal plane of symmetry in there? Well, it turns out there is going to be an internal plane of symmetry going this way. I do not have an internal plane of symmetry going vertical, because when I draw a vertical line here, the left side of the molecule is not the same as the right side of the molecule because of the double bond there. So I'll take that one out. I do have a proton here, one proton here, and then I'm going to have two protons here, and then we're going to have two protons there. So remember, the protons on the second one and the proton on the third one, they are actually going to be enantiotopic, but remember, enantiotopic protons are still going to be equivalent to one another. So if I elaborate that a little bit, I know there's two protons on number 3. So if I replace one of those protons with a deuterium, all of a sudden this carbon 3, or this third carbon right there, will become chiral, but that makes those two protons enantiotopic, but even enantiotopic protons will be showing up at the same place. Now, what happens to these bottom protons, or the protons that's on the bottom half of the ring? Well, they are going to be equivalent to what you've seen on the top. So I'm going to have 1 here, 2 here, and 3 here. So there's only going to be 3 signals at the end of the day. Moving along, what's going on with this guy right there? We have a methyl group on the top, so that's going to be 1 signal. Do we have any internal plane of symmetry here? Well, it turns out we do have a symmetry. If I draw a line here, then you can clearly see the left side of the molecule is the same as the right side of the molecule. So don't worry about this metal, because remember, that's a single bond, and this metal on the top, it can go like onto the left side or onto the right side. So we're looking at the symmetry with respect to the ring. So what's going to happen in that case, I do get 1 signal from the metal that's attached to the oxygen, because it has 3 protons in there. And then when you're going into the ring, I'm looking at 2 protons right there. That's going to be on the ortho position. They are going to be equivalent to one another. So that's going to be your signal 2. And then I have 2 protons on the meta position. Those 2 protons on the meta positions will also going to be equivalent to one another. So that's your third signal in there. And then finally, there is going to be a proton on the para position as well. So that para position proton is going to be number 4. So at the end of the day, there are going to be a total of 4 signals. Now, what their splitting is going to be, that's something we'll talk about in a different session. Right now, I just want to focus on how you predict the number of signals. Let's look at this next one. Well, what's the difference between the one we just did and this next one here? In the first one, we have only one methoxy group on the top of the ring, but now we got two methoxy groups, one on the top and the other one is on the bottom. So what that really does, so that's something you want to keep in mind. Well, remember there was already a vertical kind of plane of symmetry where the left side of the molecule was the same as the right side of the molecule. But then what happens to the horizontal now? If I draw a line here, then you can clearly see that the top part of the molecule or top part of the structure is the same as the bottom part of the structure. So you do have a lot of these protons going to be equivalent to one another. So when I write down, I would see one signal coming from the metal of these methoxy group, and that's going to be the same signal coming from the bottom methyl group of this methoxy group. And then you have another signal coming from these two protons, but then those two protons are also going to be equivalent to the other two protons you have in the ring. So there's actually going to be only two signals at the end of the day. Okay, what about something like a double bond? Well, double bond gets a little bit tricky. So whenever you have a double bond, the rotation around the double bond is going to be restricted. So if I go ahead and draw out all the protons in there, I know there's going to be a proton here, and I know there's going to be a proton here, and a proton here. And then obviously there isn't a CH3 group. So how many signals I'm going to see here? You have a double bond restriction, double bond rotation restriction where this top side, we can maybe call this proton 1 here. So this proton 1 here, and you have proton 2 here. Those proton 1 and 2, they are in a different environment than the proton 3 and the proton 4 here. So as a result, even though the proton 1 and 3 are attached to the same carbon, they're not going to be equivalent. They are going to be your distereotopic protons, and as a result, you will have a separate signal for the 1 and for the 3. And in addition to that, your 2 is also going to be a separate signal, and obviously your CH3 is going to giving you another proton signal. So at the end of the day, you're going to have a total of 4 signals in there. So remember, anytime you have two protons on a one double bonded carbons, those two protons gonna be distereotopic if the other carbon of the double bonded is going to have different substituents on it. So another way of saying, if you get into a situation where you have either a cis or trans, then you're going to have separate signals for those. The 1 and 3 is called an geminal hydrogen. 1 and 2 is going to be called an vicinal hydrogen. So those two hydrogens are vicinal to one another, and this 1 and 3 are going to be called a geminal to one another. Okay, what about this next one here? Um, I don't really see any plane of symmetry in this next one because you got a metal group on the top here and you got an OH group here, so that doesn't really give you any symmetry in the structure there. So as a result, all these protons going to be different from one another. So I will see one signal coming from here, and I can clearly see the second signal coming from the proton that's attached to the OH there. And then what other protons you have in the ring. I got a proton here, that's going to be 3, proton here, 4, 5, and 6. So there's going to be a total of 6 signals in this particular one. Okay, let's try to look at this next one. We have an alkene, we got a ketone on the top, and we got two methyl groups on the bottom. So this structure nowhere has any symmetry in there. So as a result, any proton you see in there is going to be different, except those methyl protons. So those methyl protons going to have one signal. So I'm just going to go and write down one here, and then you're going to have another signal coming from these protons right there on the left carbon. The left top carbon is going to give you another signal here, and then you're going to have 4 and 5 here. So now remember, the protons on the 3 are going to be an antitopic, and the protons on the 2 are also going to be an antitopic. But since they are not distereotopic, you're not going to be seeing any different signals for those. Let's look at this next one here. I would have a metal there, so that's going to give you one signal here. I do have a proton on this carbon that has the chlorine attached to it, so it's going to give you the second signal. The next carbon on the line does not have any proton here, but then you have a proton onto this double bonded carbon on the left side, so that's going to give you a third signal. What about those two protons you got on the top there? Well, remember those two protons on the top there, they're actually going to be distereotopic protons, because if you replace one of those hydrogens with a deuterium, it becomes chiral center, and you already have another chiral center in the molecule present. And they're going to be having different chemical shifts, or another way of saying they're going to be not equivalent. So I'm going to be seeing a fourth signal here and a fifth signal there. Now, it's very likely they may be having a very close chemical shift with one another, but you still want to be calling those as magnetically different protons in this particular case. That's going to give you 5 signals total. Let's look at a couple of these question stuff left here. I'm going to have one signal coming from the OH proton. There is a proton on to this carbon that has the OH attached, so that's going to give you the second signal. The methyl group that's coming out of the page give you third signal. And now I'm going to have two protons here on this benzylic carbon. Now this benzylic carbon, since we got two protons, it's going to be prochiral, and your molecule already have another chiral center. So as a result, those two protons are going to be distereotopic from one another, and they will give you different signals. So it's going to be 4 here and 5 here. And then in the ring, what's going on? Well, remember, your ortho are going to be the same, because even in the ring right now, you have this internal plane of symmetry that kind of goes like this. We can clearly say that I'm going to have 6 here, 6 here, and then those meta protons are going to be equivalent, so it's going to be 7 here, 7 here, and then you're going to have 8 here. So that's how many different protons you're going to be seeing, or different signals you're going to be seeing for that particular molecule. What's going on with this next one? The next one is a little bit interesting in the sense that it's got a couple of internal plane of symmetries going on. So you got a symmetry. If I draw a vertical line, then the left side and the right side of the molecule is the same. And then I can do the same thing if I draw a horizontal line, then your top and the bottom is the same. So it turns out all those protons are actually going to be the same. We're going to have the protons on those metals to be 1. And then do we have any other protons? Well, we do have a proton actually in the ring. So those protons right there, those are going to be your number 2. So there's only going to be 2 signals for this particular molecule. There's no other protons in there. What's going on with this next one here? We got a methyl group on the carbon, on the first carbon there, so I can just probably write down CH3 if you want. So that's going to give you 1 signal. Do we have anything else going along the line here? The next protons you're going to be seeing would be these 2 protons there. Those are going to be your enantiotopic protons, so they're still going to be giving you the same signal. So it's going to be number 2, and then these CH3 protons are going to be different than the CH3 protons you have on the first carbon. So those are going to be your number 3. Then finally, I got this one right there. So let's see what's going on here. So this one is going to be maybe a little bit complicated to kind of deal with. So let's just kind of break it down. We have protons on these carbons right there. I got 2 protons on these carbons right there. What else? We have the protons. We got a proton on this carbon. I got 2 protons on that double bonded carbon, and I got a methyl group there. And what else? Well, we got a proton right there as well. All these protons are actually going to be different. So if I call this 1 and 2, there's no internal plane of symmetry in the molecule, so that's going to be 1 and that's going to be 2. What about these 2 protons right there? So I'll just shade those with the brown highlight there. Those 2 protons are actually going to be distereotopic because you already have a chiral center in the molecule present. So since they are distereotopic, they will be showing up as 2 different signals. So I'm going to have number 3 here, number 4 here. What else? I can call the proton, that single proton right there, that's number 5. And then what about the two other protons we got there? Let me shade those again, maybe with a different color now. These two protons right there, they will be also distereotopic because if you change one of those protons with deuterium, it becomes in a chiral center, and you already have a chiral center in the molecule. So that's going to be number 6, that's going to be number 7, and moving along, that CH3 is just going to be by itself. That's going to be number 8. What about those two left protons now? Change the color there, maybe. These protons that are left, are they going to be the same or are they going to be different? Well, they are attached to a double bonded carbon, and since they are attached to a double bonded carbon, they're going to be distereotopic because I can, if I shade it like momentarily, like the environment that that proton has on the top and the environment the bottom proton has that's closer to the methyl group are different to one another. As a result, those are going to be again your distereotopic protons. So I'll have 9 and 10. So you're actually going to be seeing 10 signals for this particular molecule. All right, so this is how you're going to be determining the number of signals. This is going to be a good enough practice, but obviously the only way you're going to get better at determining the number of signals and then eventually determining how the splitting gonna work is by doing a lot of practice. So if you have any questions on those, feel free to leave any comments in the section below.